Sorry about the wait.
That's all right.
I got in a fight with the computer.
Yeah, I've done that many times.
It had to restart its systems, which was exciting.
Yeah.
Yeah, and the Wi-Fi is being really finicky today, so.
Okay. All right. Well, if we have any problems with audio, we can do it the other way. But at the moment, it sounds pretty good.
Yeah.
I'm not surprised it's finicky. Snow and cold tend to affect that if you have a certain type system.
We have the wire that runs outside, so.
Yeah. You guys on Comcast or are you on DirecTV?
Comcast.
Comcast? Okay.
Yeah.
All right.
All right.
Okay, so what do you have today? It's not by chance this, is it?
That was homework from last night.
Yes. I have another student who has the same teacher. I don't think he's in your class because he gives me different problems than you, but it's like he has every other one and you have every other one on that.
There are two Algebra 2 teachers at my school. There's Mr. Moore and Mrs. Moore, no relation. So he might have Mrs. Moore.
He does. I asked him whether this was a woman or a man, and he said it was a woman. And you'll notice that she tries to get funny in these problems.
I know.
Why are dogs such bad dancers? Because they have two left feet.
Oh, our teachers are so awkward. They think they're funny.
Yep. Well, whatever. So, anyway, I have a few of these. He sent me like 3 pictures last night to cover the problems they were going over. So, if you have some that you were going to verbalize, I may have them on a digital format.
Well, we took our test today.
Okay.
So we don't have any homework or no specific, new things to go over.
Okay. How do you feel like you did?
I think I did well. I had trouble with some of them, but it was the kind of trouble where it's not that you don't know it, it's that you're being stupid. So I came back later when I was feeling less stupid and I got the problem, so.
Good.
It wasn't, terrible.
Okay. Okay.
All right. So I guess it would just be wise to go over the next few chapters in the book and see.
Okay. Try to get ahead a little bit.
Yeah.
All right.
I don't know if next week we're going to be preparing for finals or learning something new, or both.
All right.
So I guess looking ahead would just.
When do you get out for Christmas break?
We have this week, next week, finals week, and then we're done. So 3 weeks.
So 3 weeks. Okay.
Yeah. So the next chapter is about exponential and logarithmic.
Logarithmic.
Logarithmic functions. Yeah.
Okay.
So.
All right. Let's talk about one thing before we even get started.
Smoky functions.
Exponential functions are not algebraic functions. They cannot be solved algebraically. In other words, if I said 8 is equal to 2 to the 3rd power, well, that's true. But if I said 7 was equal to 2 to the x, you would not be able to solve that for x.
Okay.
So obviously x is going to be less than 3, greater than 2, but there's no method that we have for solving that other than by use of logarithms. So that's the reason we have logarithms, is to solve exponents that aren't integer exponents. Now, if this is the exponential expression right here, as was my 8 equals 2 to the 3rd, that is an exponential expression. If you want the equivalent logarithmic expression, what is it? What is the logarithmic expression for that exponential expression?
No clue.
Okay, well, the secret is that logs are exponents. If you remember that and that alone, it will always tell you how to convert an exponential function to a logarithmic expression. If logs are exponents, and I know that the log has to be equal to x, well, the base always goes right here. The only thing left is the argument of the logarithm, and that has to be y. So these two things that I have circled are equivalent. In other words, 8 equals 2 cubed. I could also say that the log base 2 of 8 equals 3. So these two expressions are equivalent also.
Okay.
That's the first thing you need to understand about logs, and it's huge. Now, for the sake of inverses, they restrict the domain of B to positive numbers only. So B can't be negative. So this provision is always made whenever you're talking about logarithms, is that B is always a positive number. In other words, it doesn't make any sense to take the log of a negative number. Saying that the log base 10 of minus 2 is equal to something, that's like taking the square root of a negative number. You can't do it.
So there's no i's?
Well, there is I. Yeah, no, you're absolutely right. That's what you get when you take the log of a negative number is I, imaginary results. But at any level less than linear algebra and differential equations, which you get in about the third year of college, we don't tend to talk about imaginary numbers as solutions for logarithmic equations. We talk about them as solutions for square root, quadratics, but not logarithms. Pretty much they tell you got to take the logarithm of a positive number. And in fact, you can't even take the logarithm of 0. You can take the square root of 0. That's equal to 0. But the log of 0 doesn't exist. Does not exist. So your domain on the log function is actually more restrictive than your domain on the square root function.
Okay.
Why can't you take the log of 0? Well, how is y ever going to be 0? In other words, if y is equal to a positive number, b, to the x power, there is no x that produces a y of 0. If I take any number to the minus 1 million, it's still a positive number. And of course, if I take it to the plus 1 million, it's a big positive number. So it doesn't matter as long as b is positive, even if x is negative infinity, anywhere from negative infinity to positive infinity, y is always positive. It's never 0, it's never negative. So when we look at the logarithmic expression of that exponential expression, this has to be positive.
Okay.
Okay, so that's the most important thing to understand about logs, is how to convert from exponential expressions to logarithmic expressions. So let me give you a little practice. There's the exponential expression. Give me the logarithmic expression.
Okay, so it would be log equals, so you have x on one side, so that would be...
Well, no, I don't have an x or y. I've put everything in terms of numbers.
Little formula thingy. So
Okay.
then you have base 10,
Okay.
and then y would be 100, and then is equal to 2.
Correct. So this expression is exactly the same as this expression. And in fact, if you look up the common log of 100 in your calculator, it'll give you 2. Okay? Common logs are base 10. You can have log base 7. In other words, if I gave you this, give me the exponential expression of that.
You would have 49 is equal to 7 to the power of 7 squared.
Yeah, the way I like to do it when you're going back the other ways, in other words, once you get into logarithms, you want to go both directions, because you have to go, they're going to give you problems that go in both directions, okay? So when I have a logarithmic expression and I have to express it as an exponential expression, I take the number on the far left, raised to the power of the number on the far right, and it's equal to the number in the middle. In other words, over here. So that's how we go back and forth between logs and exponential expressions. And that's the most important thing you can understand initially about logs. So in your first chapter about logs, are there any exercises at the end of that first chapter?
Yeah, simplifying expressions. Whoa, is this the right chapter? Yeah, I guess.
Yeah, let's look at some of them.
All right.
Give me one of the exercises, and then I'll know how much to teach you about logs.
So some of them say just simple things, like simplify, and then it says each one to the power of 1/2.
Say again?
So some of them say simplify, like
Okay.
81 to the power of 1/2 would be 1.
Okay, so what is that equal to?
Okay. So I don't remember doing this, and I'm confused here.
So if I said that was equal to x, that's the exponential expression. So what would the logarithmic expression be?
Well, okay. It would be 81, 1 as the base, right? No, because...
Well, actually, logs are exponents, so that log is that, and the base is 81, and so x would be there. So this would be the logarithmic expression, this is the exponential expression. But to answer this, what is 81 to the 1/2 power the equivalent of? That's the equivalent of the square root of 81. So that's equal to 9.
Oh, okay.
Okay? So the logarithmic expression becomes the log of 9, the log base 81 of 9 equals 1/2. In other words, 81 to the 1/2 power equals 9. Okay. What's the next one?
27 to the power of 1/3, so I guess that's 3. But...
So we know that's 3. So that's the exponential expression. What's the logarithmic expression?
Okay, then you would have is equal to 1/3 would be the first thing.
Okay.
And then 27 3.
Yeah, this always is your base. And this is the argument.
Okay.
Now, that's pretty straightforward as a first understanding of logarithms. Let's go a little further. Log, there's three really important rules. The log of two things multiplied together is equal to the log of that plus the log of the second thing. In other words, if I said, what is the log of 2 times 3, it would equal the log of 2 plus the log of 3. This is the way slide rules used to work. They multiplied by doing addition.
Okay.
Similar to exponents. If this looks familiar, it should, because if I had b to the x times b to the y, it's equal to b to the x plus y. So the same three rules that apply to exponential expressions apply to logarithmic expressions. The second rule is this one. In other words, when you're doing division inside the argument, you can break it apart and make it subtraction. And the third rule is if you are doing exponentiation, that's the same as multiplication. So these are the three most important rules for dealing with logs. You want to memorize these well.
So it's just b for the last one? No.
It's b times the log of a. Let me give you an example for each one of these. I gave you an example for the log of 2 times 3. Well, let's take what is the log of 7 divided by 5. Based on rule number 2.
So you have log 7 minus log 5, so log 2?
No, you have log 7 minus log 5. In other words, you would have to look up in your calculator what log 7 is, and then subtract from that log 5. And that would give you the same number as if you looked up the log of 1.4. In other words, if you looked up the log of 7/5, you would get the exact same number as if you took the log of 7 and subtracted the log of 5. Each of these converts to a number. In other words, when I say the log of 3, that's a number that I can get out of my calculator. It's like saying the square root of 17 is a number. Okay, so don't be mystified by logs. Logs are just numbers. Okay, an example of the third rule would be if I had the log of x squared, that's the same thing as 2 times the log of x.
Okay. Are logs like tangents and things like that, where like it has some greater meaning that you don't really need to know?
No, they're called transcendental functions, and yes, they are. Tangents and sines and cosines are transcendental functions, and so are logs. And they're called transcendental because they're kind of like a derivative function. In other words, logs come from exponential expressions, and sines and cosines come from ratios of triangle sides. So they're not direct functions, they're called transcendental functions. But they become extremely valuable for doing higher math, for doing calculus and stuff. And let's talk about one other thing about logs. This base. You can have any base you want. When I write the log of a to the b power, if there is no base indicated, it means base 10. In other words, the log of 5 is the same as the log base 10 of 5. The log, if I want to use a different base, say 7, the log base 7 of 49 is 2, because 7 squared equals 49.
Okay.
So there's different designations. If you don't see a base, it means base 10. The two most common bases are base 10 and base E. When you see this expression here and you look on your calculator and you see that natural log, what that means is that's the same as the log base E of E. When you see natural log, it's a base E, and E is equal to, it's an irrational number, so it goes on forever like pi, but it's approximately equal to 2.71. And E is one of those numbers that is, it's probably the second most important number in mathematics behind pi. If you were going to say there's only two really special numbers in mathematics, it would be pi and E. Both of them are irrational, and both of them are weird, and they both have enormous implications in the world. So natural log function is the big one. Once you get to calculus, you only deal with natural logs pretty much. You hardly ever deal with logs that are a base other than E. And when I said that the natural log of E was equal to 1, why is that? Because E to the 1th power is equal to E. Couple of other things about logs. The log base anything of that base is always equal to 1. So if I said the log base 18 of 18 has to be 1, because 18 to the 1 power is equal to 18. So it doesn't matter what B is, the log base B of B is always 1. Similarly, the log base anything of 1 is always 0. In other words, the log base 19 of 1 is equal to 0, because 19 to the 0th power is equal to 1. And in fact, any number to the 0th power is equal to 1. So the log of 1 is always 0, no matter what its base. Alright, I've just taught you, I think, probably everything you need to know about logs, or that you will learn about logs. You may go a little further than that in your class, since it's honors algebra. But what other kind of problems do you have at the end of that first chapter about logs? We're starting to have an audio difficulty here. I'm getting some choppiness. Close out some of my stuff here. Sarah, can you hear me?
Yeah, there we go. A little better.
All right. I didn't hear what you said. What
well, I was saying I couldn't hear what you were saying.
Oh, okay. That's funny. Yeah.
Okay. So the problems from the chapter?
Yeah.
So some of them are things like radicals. Then there's solving little equations that they use.
Okay.
And simplifying expressions. So,
okay.
I guess simplifying some expressions.
Yeah, let's start from the beginning. Since we're getting a little bit ahead, we don't want to start at the end. Let's just start from the beginning and go down.
Okay. So one of them says a to the power of 1/2 multiplied and then parentheses. So times a to the power of 3/2 minus 2a to the power of 1/2 and the parentheses.
We're simplifying that?
Yes.
Okay.
And then give answers in exponential form.
Okay. This is not really a logarithmic problem. This is an exponential problem.
Okay. So my
That's
book is
fine.
wrong.
That's fine. So let's distribute this. What is a to the 1/2 times a to the 3/2?
A to the 3/4.
You add the exponents. So 1/2 plus 3/2 is 4/2.
Oh, sorry, multiplication. Yeah, is 4/2.
Right. In other words, when you're doing multiplication, you add. Okay, and what's the second term?
Second term would be negative 2a to the 1/2.
To the 1.
The 1.
Yeah, we're going to add this 1/2 to this 1/2, and we get 1.
Yeah, okay.
So this is the simplification of it. A squared minus 2a.
Okay.
Okay? All right, so this chapter is just a real basic introduction. It sounds like the exponentials.
Okay,
So,
just go a little
yeah,
deeper.
go a little further. Let's get a little bit more higher degree of difficulty here.
So the next chapter...
Either the next chapter or harder examples in that same chapter.
The next
We don't want to get you too far ahead.
Yeah, little there's like little sub chapters.
Okay.
Like there's chapter 10 and then part 1, part 2, part 3.
Okay.
The next little part of the chapter has pictures of graphs and then more exponents.
Okay.
Growth of functions, the composition and inverse of functions.
Okay.
It has. Should we do those or?
Yeah, I think that you'd be better off learning logs before you learn about inverses.
All right. Oh, I found the logs.
Okay, and the only reason I say that is because there's one very confusing part about logarithms. And that is that the log happens to be the inverse of the exponential, but not in the way that it was stated. In other words, if I say y equals b to the x, well, that's the same thing as the log of y base b is equal to x. But if I wanted the inverse of this, then I would say y equals the log base b of x. This is the inverse of that. It is not the equivalent. That's the inverse. And because that's one of the most important things about logs is that they are the inverses also of the exponential expression. They teach it as the beginning, but it must have taken me until like the third year of college before I realized the difference. I was always confused by the inverse expression and the equivalent expression. Notice that they are not the same. They are completely different. The x and the y's are reversed.
Okay.
Okay? So it is kind of important to know that a logarithmic expression is the inverse of an expression. Let me show it to you graphically. Since they're going to put that in that second chapter, I guess we better go over it. If I wanted to draw that equation is y equal b to the x. There's your exponential expression. Well, it turns out that there is an inverse of this. And remember, inverses are always reflections about the line y equal x. So the inverse looks like this. notice that this curve is y equal log of x, log base b of x. That is not the equivalent expression, but it is the inverse of it. And it's the perfect inverse. So for every exponential expression you want to talk about, you can look at the inverse expression. But do not confuse this with the equivalent expression. For most of the first 2 or 3 chapters you're going to take, it's going to be all about equivalent expressions. You're not even going to know that one is the inverse of another. And I think it's best to leave that until after you've done the rest of logs myself. Logs are hard enough to do without dealing with the fact that they're an inverse function also. Typical things that you're going to have to know are things like expand this. Using those 3 rules that I referred to.
Okay.
So let's do it one step at a time. Let's take the fact that we're multiplying 2 things together. Let's separate those into the addition of stuff. So what's the first thing I can do?
So you can do the log of x squared plus the log of b.
Plus the log of y.
Oh, sorry.
Okay. Now, this exponent I can take and move to the front. So that becomes this. So this would be the expansion of that. And they want you to be able to go both ways. So they will give you a section on expand this, and then they will give you a section on contract that. In other words, you start from this and you put it back into this form, or you go the other way. So a harder one might be the following. Expand that.
Okay, so then that would be equal to the log of the square root of x times y
Plus
plus y cubed?
not times.
Oh, sorry, plus y cubed. And then minus log z to the power of 4. Z.
Correct. And now the second step would be, that's the same as the log of x to the 1/2, so I can take the 1/2 and put it in front. I can take the 3 and put it in front. And I can take the 4 and put it in front. So that's fully expanded. And they'll want you to be able to go both ways. They'll want you to be able to contract expressions and expand expressions.
Okay.
Okay? Without knowing how fast they're going to take you through logs, let me just throw out a few other things here.
Tricky.
Let me think a second here. Solve that. In other words, this is a logarithmic equation. And you're going to solve logarithmic equations by using those 3 rules for contracting and expanding. This has been expanded, so let's contract it. What's this the equivalent of?
That would be, well, since it's added like that, you know it's multiplied.
Right. So it's the equivalent of x plus 1 times x minus 1. And that is x squared minus 1. And now, in order to solve this, put it into exponential format.
So then you get...
This is assumed to be base 10.
Yeah. So it would be... One second. I can't read my handwriting on my note card.
So think of it as the number on the far left raised to the power of the number on the far right. So 10 to the 0th is equal to x squared minus 1. And what is 10 to the 0th?
That would be 1, right?
So now I have 1 equals x squared minus 1. Now I have x squared equals 2. And now I have x equals plus or minus the square root of 2. So there's your solution. But with logarithms, you always have to be very careful of the domain. Notice that one solution is plus 1.41, the other solution is minus 1.41, and if I substitute the negative solution in there, it violates the domain right there. If I use the negative solution, I'm taking the log of a negative number. You can't do that. So this negative solution is extraneous. We're only going to use the positive solution. So the positive solution is plus 1.41. Doesn't violate either domain. And it's true that if you put this into your calculator, the log of 2.41 plus the log of 0.41, you will get something very close to 0. I say close because I'm approximating with these numbers. There's going to be some round-off error. So that's how you solve logarithmic equations, is by using these 3 rules for expanding and contracting logs and then converting it back to an exponential expression that you know how to solve. In other words, once I got it to this, I was able to say 10 to the 0th power, or 1, was equal to x squared minus 1, and then I can solve that. That's an algebraic equation there. I can solve an algebraic equation by taking the square root of both sides.
Alright, so it's just like regular equations on steroids.
It is. It's like regular equations on steroids. The only thing is that you almost always have an extraneous solution. Unlike a polynomial, you know, if I give you x squared minus x minus 6 equals 0, well, I get 2 solutions, x equals 3 and x equals minus 2. Well, both of those are true. Both of those work. There are no extraneous solutions in most polynomials. Where you end up with a lot of extraneous solutions is when you see radical signs in equations. In other words, if I have an equation that says the square root of x squared minus 3 equals 7, and you go to solve that, you're liable to come out with 2 solutions, and one of them will be extraneous. It won't make sense. It won't work. So the place where you find extraneous solutions is when you have radicals, when you have absolute value signs, or when you have logarithms. And that's a good thing to know. because it means you don't have to waste a whole lot of time checking both solutions when you have just a standard polynomial like this. You're not going to find an extraneous solution. But when you're solving logarithmic equations, you almost always, one of them will be extraneous and have to be discarded. And the curious thing is that you have to go back to the original equation to find out whether it violates the domain. You cannot go to that equation. So when I say the log of x plus 1 plus the log of x minus 1 is equal to the log of x squared minus 1, it's not 100% true. It's not equivalent in the sense that their domains are the same. You can never violate the domain of the original function no matter what. In other words, if I'm solving that equation, even though I have to do it this method, and I get two answers, in order to see if I violate the domain, I always have to go back to the first equation, the original raw equation, not this. And the reason logs are so important is because the derivative of 1 over x is equal to the natural log of x. That is one of the most important fundamentals of calculus.
And the natural and derivative logs, what's the meaning?
It just means that the derivative, well, it's hard to explain what derivative is to you in a paragraph. That's the essence of calculus, is teaching people what derivatives mean. It's basically the instantaneous rate of change, but when you take the derivative of 1 over x, you get natural log x, and that is huge. That becomes the pathway to solving all kinds of higher mathematic problems, and that's why logs are such a big part of math. But more than that, in other words, when I mentioned before that about a slide rule, you probably don't even know what a slide rule is, but we were forced to buy one in my first year at Mines. We had to go out and pay 80 bucks for a slide rule. And a slide rule would allow you, it was like a calculator, but it allowed you to multiply numbers, because each part of the slide rule was in a logarithmic scale, not a regular scale, so that when you added one log to another, you were really multiplying numbers. And so if I took the log of 2 and I added it to the log of 3, which I could do by just moving one of the pieces of wood relative to the other, well, I know that that's the same as the log of 2 times 3. So my answer, when I added the log of 2 to the log of 3, gave me what was 2 times 3. So you could use this slide rule to do multiplication and division. And that's a beautiful application of logarithms. And that also has lots of calculus implications, because it's hard to take derivatives and integrals of products, but it's very easy to take derivatives and integrals of sums or differences. So if you can take a function and convert it from product to sums or differences, you've made a lot of progress.
Okay, so it's just...
Yeah, I'm getting way ahead, but I don't know what else to tell you about logs. I've given you kind of a full course in logs in 40 minutes here. But hopefully it'll make more sense to you when the teacher goes to explain it to you.
Right, so it's like a nice little crash course.
Yeah, exactly is what it was. It was a crash course.
Okay.
But it seems like you picked it up pretty good. You know how to expand and contract, and that's a big thing. In fact, solving logarithmic equations is the last chapter on logs that you'll have to do. So we kind of went through the entire chapter today.
All right.
Okay?
All right.
All right. Well, if you don't have any other questions, I'll let you go.
Okay.
And I'll get on with David here in a few minutes.
Before you go, David
Uh-huh.
managed to screw his phone up royally somehow, because
Okay.
our whole family is technologically challenged. It's terrible.
Okay.
But so he said that if you could send the code to my number, that it would be
Okay. I'll do it.
All right. Thank you.
All right. Bye-bye.
Bye.